Hello, welcome to the Wolfram U course Quick Start to Wolfram Tech. We are just doing a quick mic check and allowing everyone to get into the webinar room. We will get started in about 10 minutes. Hello, everyone. Welcome to the Wolfram U course Quick Start to Wolfram Tech. My name is Abrita Chakravarti, and I will be your instructor for today. In the chat pane to the right of your browser, you will see a sticky note with a link to a zip of all the handouts. You should have also received the link in the reminder emails for the webinar. So if you would like to follow along in your own notebooks as we move through the course, you're welcome to download the zip and extract the notebooks from there. We have 4 notebooks for today. We start out with a few examples showcasing Wolfram Tech, and then we start with the basics of working in a Wolfram notebook. And the third notebook or the third handout will deals with content that explains how to use the Wolfram language. And then the final handout is a hands on exercise notebook that you can try on your own. It has questions, hints, and solutions, so you will be able to work through some problems using the Wolfram language and the Wolfram tech. So, without further delay, let's get started. I'd like to start with a short poll to get to know a little bit about you. So, if you wouldn't mind answering the poll that appears on your screen right now, I'd like to know if you have been using Wolfram technology for a while or you're a brand new beginner in Wolfram Tech. If you've used certain aspects of the technology but not the others. We have a small group with us today, so if you have any questions during the course, please feel free to put them in the questions pane. It should appear just below the chat pane. Um, what I can do is I'll take little breaks in between the notebooks, and then I can try to read out the questions and answer them. Um, uh, Even if I'm unable to stop for the questions during the presentation, please feel free to put them in because they get recorded and then I can take a look at all the questions together. All right, thank you for your response. So I see we have a mix of folks who have created Wolfram notebooks but have not really explored the other resources, who have viewed or interacted with notebooks or programs created by others. And then we have at least one beginner who has never used Wolfram technology. So, welcome to all. Let's get started with a few examples. So, in this very first notebook, I'd like to talk about the Wolfram technology stack, introduce a few of the technologies and products that we have, so you are aware of the many different ways you can use Wolfram Tech. And then I want to showcase a few examples of using the Wolfram Tech for various computational explorations. I have attempted to select these examples across different topic areas, and so we can look at an example of mapping the position of a satellite and then move on to maybe closing prices of stocks or visualizing the human neural network. Um, in the interest of time, I might not be able to get into the details of these examples, but they are there in the notebook. So I hope you're able to take a look at them and explore them a little bit. And then I'd like to end with some of the resource we have for the new Wolfram user, some of the options available through the use of Wolfram Tech for natural language understanding, taking advantage of a great collection of state-of-the-art algorithms using the Wolfram Cloud and some of the other Wolfram resource systems like the Wolfram Data Repository or the Wolfram Neural Net Repository. So when we talk about the Wolfram technology stack, there are several components. Let me introduce just a few. So at the heart of it all is the Wolfram language. It's a high-level symbolic knowledge-based programming language that we hope is easy to use. And not just that, it also allows the new user to take advantage of a lot of power built into the language, whether it's just built-in knowledge or really sophisticated algorithms. Now, how do you use the Wolfram language? So one user-friendly interface is the Wolfram Notebooks, which provides an environment where you can type in the code, evaluate it, and see the output. And as you will see in the very next notebook, very next section of this course, a notebook can contain Wolfram language code, text, images, interactivity, and much more. Then the Wolfram language is also used in creating programs that then can be run through the Wolfram engine. So the Wolfram engine is really a software engine implementing the Wolfram language, and it is at the heart of Wolfram products like Mathematica, Wolfram One, or even the Wolfram Alpha computational search engine that you might have used, might have access through the browser. So it's really the Wolfram engine that's running behind it. And it can be called from command line as a script, or through sockets, or through client libraries for Python, Java, and so on. So you don't need just the Wolfram notebook to work with the Wolfram engine. And then another part of the technology is the Wolfram Cloud, which is the central infrastructure for all cloud products and services that Wolfram offers. It can be installed as a private instance, as enterprise private cloud, or accessed through a cloud basic plan. So if you have used the link we shared for Wolfram One, the trial version, then you will have access to the cloud basic plan, and you should be able to open up a browser and then start working in the Wolfram Cloud. So beyond these technologies, there are a number of products available from Wolfram which allows you to access these technologies. So primarily, we have lots of users using Mathematica either through their school or work or their private licenses. So this is the Mathematica is an integrated system for technical computing. You do have the option to access it through the cloud as part of Mathematica Online, or you can definitely use it on your own desktop. And then we have Wolfram One, which is a sort of a cloud desktop hybrid computational platform. It's actually offered as an ideal entry point for the newcomer. um, you can start off in the cloud, log on to Wolfram One in the cloud, and then you can also choose to continue to work offline. You can download your notebooks on your system and then continue to work on it offline. And then, of course, there's Wolfram Alpha, the computational knowledge engine I mentioned earlier. You can access it through the server, through your browser, and you can look at a lot of computational stuff here that which you can later recreate in the notebook. So I'm going to start with a few examples, and for the newcomers, my request is not to get lost into in the details of the code. I'm showing a bunch of things, and there's quite a bit of code on these slides, but my intention is really to get you excited about the stuff that we can do with the Wolfram Tech. And if there are parts of the code, snippets of the code that don't quite make sense, my request is hang in there. We will look into the details of the syntax of the code in the later section of the course. So let's just enjoy some of these examples just to see what is possible with Wolfram Tech. For my first example, I selected this computational exploration that looks at the position and path of the International Space Station. So in the Wolfram language, you can actually find more information about satellites. So for example, I can figure out the position of the International Space Station right now. And this is the geopositions given as geographic coordinates. And then I also have the ability to specify for which date exactly I want the position. So instead of now, I could use some other specific date on time, and I could find the position, which is what I did when I was preparing this notebook. And then not just the position itself, but the entire position line that is tracked by the satellite in 24 hours. And so here I get that entire position line, a collection of geopositions, which tells me how the satellite has moved. And then, of course, once I have the current position and the position line, I can visualize it. And here's an example where I see this is how the International Space Station moved over the Earth in the last in the 24 hours since I evaluated the code. So it shows the track as well as the current position when the code was evaluated and the geovisible region or from that position of the satellite. Um, so a simple example of getting information and visualizing it. Here's another example, tracking the cumulative returns of stocks. So I can either use natural language understanding and see how these stocks are represented in the Wolfram language. And you see it's converted into the Wolfram language representation of these financial entities. So in the Wolfram language, you have something called entities, and we can have entities of different types. Right now, you are seeing financial entities, a collection of financial entities on your screen, which I've grouped together in as a list of stocks. And once I have these, I can then obtain specific properties of these stocks. So I have chosen to get the cumulative fractional change to see the cumulative returns over last 90 days. And then I've specified the date range here, and I get back time series of the values for these 90 days. And once I have them, I can go ahead and create a visualization, not just a static visualization, but I can create an interactive visualization which allows me to pick one stock and then pick another one and then compare their cumulative returns for those 90 days. Moving on to another example from a very different area of study, biology, here's an example that visualizes the human neuronal network. Again, I'm making use of entities in the Wolfram language. So there is an anatomical structure entity, and in this case, I'm using specifically the amygdala, an anatomical structure entity. It has a property called neuronal output, which shows the connections really to all the other regions of the brain from the amygdala. And now once I have these other regions, I can actually create a graph out of it. And so here I have an example where I'm creating a visual graph with the amygdala in the center and all these other regions of the brain that it is connected with. I know there's a lot of code that's included in these examples, but again, my request is stay with me. We are just looking at some of the things possible with the Wolfram Tech, and we can get into the details of the code a little later. There are a few other examples. There's one in physics that visualizes the colors produced by lasers in the visible spectrum, which has wavelength in the visible spectrum. And then another one in geography, where you can visualize shipwrecks along with undersea features in the Mediterranean region to see if there is any correlation between shipwrecks and the undersea features, if something under the water really caused the shipwreck. There is also an exploration in history, which allows you to visualize a historical country. So earlier on, we saw a map visualization of the ISS as it was moving above the Earth. But here is an example of something from the past, a visualization of the Roman Empire as it existed in the year 0. And then it is also possible to actually get the information about the areas of the historical countries and pick the 10 largest countries in the year 50 AD and then visualize them here in the map to see where these countries existed in the current map of the world. And then the last example I have is from literature, and it walks you through how you could do some computational analysis of text. Now, if you went to the Wolfram Alpha browser and typed in Romeo and Juliet, one of Shakespeare's more famous plays, you will already get a lot of computational input. So you will see, along with the details of the play, like the title and the author, of course, you will see a lot of computational information like the number of words, number of unique words, number of the average word length or the longest words in the text, along with a lot more information. So, for example, the total number of words spoken by the characters or the number of appearances by that character in the play. Now, along with this information, that is presented in a nicely formatted way. If you wanted to analyze that text, that is also possible. So you can import the text and then do analysis like find the positions of a specific string in the text. For example, if you wanted to find the position of the word Romeo in this piece of sentence, or Romeo, Romeo, wherefore art thou, Romeo, we can do that with string position. Now, what we can do for one sentence, we can do for the entire text of the play. And so here is an example where we can find the location of Romeo in the entire text. So it gives the starting and the ending position everywhere the word Romeo occurs in the play. Now, what we can do for one word, we can do for multiple words. So along the entire text of the play, we can look for the locations of the words Romeo or Juliet, and maybe life and death, really any word of your choice. And once we have those locations, we can visualize them. So it kind of shows us, as the play progresses, who is being mentioned a lot more. So here we see, in red, we have Romeo, in green we have Juliet, how they are mentioned as the play progresses, and how the words like life and death in the blue dash line and the orange dash line are mentioned as the play progresses. And so, of course, if we can do it with one set of words, we can do it with another set of words. And then a little more computational analysis, we can get the sentences from the play and then do something like sentiment classification. So we try to identify if the sentiment of that particular sentence is positive or negative. And once we have classified if the sentence sentiment is positive or negative, we can again plot it along the timeline of the play and see which parts of the play has more positive sentences and which part of the play has more negative sentences. So a few examples of really simple computational explorations. Um, Moving on from there, I wanted to check in with you about some of the resources really available to the new Wolfram user, so that you do not always have to build everything from scratch or write everything from scratch. There are certain resources we have available with the Wolfram Tech, like natural language understanding or the collection of algorithms, or the cloud system for deployment of APIs or forms and applications. And then finally, we have the resource system with a built-in collection of models or data that I hope you will be able to use. So the first is, of course, natural language understanding, and we'll see more examples of this in the next sections. So I did want to highlight that even if you're not sure how to write code in the Wolfram language, it is easy to get started because you can just enter your query in plain English. So for example, I can just enter GDP of EU countries, and then it gets converted into the actual Wolfram language representation, which is European Union countries and GDP as a property, and then I'm able to get the output from here, even if I am not quite aware of the Wolfram language code that needs to be written to get this output. I can even go on to say things like plot the GDP, and then the system is able to interpret this as a request for a bar chart and able to work with that and give me the bar chart. So I didn't actually have to write out the code to create the bar chart. And then there's another example for a different sort of visualization. About the collection of algorithms, uh, you might be aware of the traveling salesman problem, which is a very famous problem in computer science. And it's stated as given a list of cities and distances between each pairs of cities, what is the shortest possible route that visits each city and returns to origin city. It has many applications in logistics, planning, even area like DNA sequencing. So it's a complex problem, and in the Wolfram language, we have a single function that is able to implement the solution to the problem. And for the new user, instead of having to really uh, write out, worry about the implementation logic, you are able to use that function just as a representative of many such sophisticated functions that are available in order to use it in in your particular project. So the example that I show here is that in case you wanted to find the shortest tour of all the capital cities from European countries, then we can just use find shortest tour on a list of those capital cities that is given by um, this part of the code. And then you can not only just find the tour, not only find the ordering of the cities that minimizes the total distance on the tour, but also you can visualize it using GeoList plot. So we can go ahead and try that. And it just gives a the numbering of the cities. So if you're interested, we can just evaluate this separately, and we'll be able to see the mapping of the index and the city there. But once we have this information, we can go ahead and use GeoList plot to visualize it. And here we have a solution to the traveling salesman problem. Two other things that I wanted to point out is using the Wolfram Cloud. So here I have an example of how you can use the Wolfram Cloud to build a dashboard. This is a really simple dashboard that shows the weather of a place. So the way this has been done is Wolfram language code has been used to first get information about temperature, humidity, wind direction, and wind speed of a place with the help of a Wolfram language function. And then each of those information is presented in the form of an icon, one of these four icons, and they are put together neatly in um, in a graphic arrangement with rows and columns to show the information about the weather. And the way that is done is by deploying an API function with this code that creates that little dashboard. And then it has been deployed with public permission. So if you have the notebook, you can click on this link and see an example of this deployment. So it currently shows the temperature in Champagne here, and the humidity, as well as the wind direction and the wind speed. And then there's another example that actually deploys a form instead of an API, where it just deploys this little form. Again, you can access it from the link that is provided in the notebook. And you have this little form here where you can pick an image and then apply an image filter to it. And you will notice in the code here that the code is really not too much. Like in very few lines of code, we are able to deploy this simple app. And here we have the filtered version of the image that we provided. And then the final part of this section of the course about the Wolfram resource systems, I wanted to point out that we have the Wolfram data repository. And again, it is linked from this notebook. You will notice that you can go to the Wolfram data repository and, for example, you can go to the one of the different multiple data sets available on the Wolfram data repository. You can also browse by category of data or the type of data that you want. And each of the data resource items on its page has a bunch of examples that shows you how to work with that data resource. So for example, for the meteorite landings data set, you will not only find the code to access that data resource, but also some sample code to see how you can work with that data resource. For example, for the meteorite landings, you can see where in the world they landed, and so you can visualize it in a map. And that is what I show here. Is once you use that code, you are free to go ahead and edit it and try it out for a different place. That's an example of using a data resource. There is also the Wolfram neural net repository. And again, This is available on the web, and you can go to any of the models available on the repository. And again, you can browse either by input domain or by the task type, and you can go to the specific page for a particular model, and along with the code to access the model, there will be other examples to show you how you can download the model and use it yourself. And this is the example that's shown in the notebook as well, where we download a trained neural net model that was trained on the MNIST dataset that recognizes images of handwritten digits and is able to identify them as the digit itself. So you can download that in neural net, and you are able to use it on your own images. Along with these two repositories, there's also the Wolfram function repository, which is a collection of functions contributed by many Wolfram users, along with folks at Wolfram itself. Our greater community of Wolfram users have contributed functions to this function repository, and if you're interested in browsing it, you will find many interesting functions, things people have found really useful, and were nice enough to package it into a nice function and make it available for the others in the community to use. So that brings us to the end of this first section of today's course. I have ended with a few references to multiple resources that should help you get started using the Wolfram language. As we move to the next section of the course, where we will work within a notebook, I have a couple of questions for you. I was wondering if you might let me know which of the following are you most likely to explore as you get started with Wolfram technology. I tried to show you a few different aspects of the technology. There were the notebooks, the natural language understanding capabilities of the language, um, built-in functions as part of the collection of algorithms available. There are also the resources like the data repository, the neural net repository, or the Wolfram Cloud, which can be used for either publishing your own content or deploying apps. All right, thank you for responding. So I see more interest in using the Wolfram Notebook as an interactive programming environment, and also as an environment for creating and documenting technical workflows. And I do see at least one other person interested in Wolfram Cloud for publishing content and deploying apps. So that is great. So maybe we'll focus on those two aspects of the technology a little more. Um, I did have one other quick question. So, since you're here, I'm assuming you are interested in using Wolfram technology. So, how really are you planning to use Wolfram technology in your work, in your next project? Are you planning to work on some computational explorations, or are you interested in some data science analysis? Do you have a very technical workflow in mind? So, probably some sort of scientific computation, or are you interested in developing an application, maybe deploying it on the web? Or maybe you are exploring. That's fine as well. Uh, that's a wonderful place to be, to explore all the different technologies available and then decide later on how you want to use it. So that's great. Thank you for your responses. All right. So for this next part, what I would like you to do is, if possible, if it is possible to for you to have two browsers open, two browser windows open simultaneously, you're welcome to work along with me. We will work in a Wolfram Cloud notebook, or if you would like, you can follow along with Notebook 2. It looks like this. That's it's called the basics. And I have included screenshots in this notebook. So even if you just look at the presentation right now and don't work or want to work on it yourself, you should be able to follow along with the screenshots later on your own, at your own pace, and then revisit some of the things that we do today right now. So I would like to introduce you to the Wolfram Notebook and the many features of the Wolfram Notebook, how you can work on it. We'll start in the Wolfram Cloud. So if you will go to wolframcloud.com, you can sign in from there, and then you can go ahead and open a new notebook. I'll give folks a little moment to sign in, and if you're interested in working along with me, to sign in and get set up with your new notebook. Okay, so once you have your new notebook open, what can you put into your new notebook? So of course you can put in Wolfram language code. So something as simple as arithmetic. So we can go ahead and evaluate 2 plus 2. And the way you evaluate Wolfram language code in the notebook is by hitting Shift Enter. And once you hit Shift Enter, the code will be evaluated and you will get back the results. So you can try 2 plus 2, or you can try something like range 10, which will give you a list of 10, the first 10 integers. And then you can use just take range 10 one step further and use bar chart on it, so that will visualize these numbers in a bar chart. Really simple stuff. Okay, so these were examples of how you can include Wolfram language code in the notebook. Now, in addition to this, you can also include text. And to the way we are going to include text is we are going to click just above the first input that we provided, 2 plus 2, and you will see this little plus sign over here. It's a little hard to see in the browser, but if you just click above 2 plus 2 in your notebook, you will see the little plus sign overhanging here. If you click on it and then select plain text from here, it will start a plain text cell for you, and then you can write something about the code that you wrote. And so, for example, I can write calculate the result of adding 2 and 2. Really just a demonstration of how you can include text to add context to the code that you're writing. So I can say create a list of the first 10 integers, and so on. Okay, so we added Wolfram language code, we added text. We can also add images and graphics. So for one, we can again use the natural language understanding abilities of the Wolfram language. So I can type in control equal to, which will give me this little box with the white equal sign in an orange box. And I can type in image of a gray wolf and hit enter. In this case, I just hit enter because I entered the query in the natural language, not in the Wolfram language. And once Wolfram language recognizes what I have entered, it says, is this what you meant? And I can click on the little check to indicate, yes, this is what I meant. And now I have a Wolfram language code here. And you know how to evaluate Wolfram language code, right? So we will go ahead and hit Shift Enter, and I will get back the image of a gray wolf. So you can see it's a little low resolution, but it's much better on the desktop notebook. So this is one way you can have an image in here, or I could even go to a website, and then I can, let's see, I can go ahead and copy an image. Let's see if I can find a nice image here. Um, let's see, this is interesting. Computational origami. Um, maybe not. I'm not having a, a good time finding a nice image. So instead, what I'm going to do, I'm just going to import one of my pre-decided images. So I'm going to import the image of Wolfie from one of the Wolfram pages, and then I am doing it by using the import statement. You can copy this statement from the notebook 2, the basics, and you can go ahead and evaluate that, and it's going to import that image of Wolfie and put it in the notebook here. What I was trying to show you is you can basically copy and paste an image from a website into the notebook as well if you wanted to. And then, of course, we also have other functions in the Wolfram language that create visualizations. So you should be able to try those as well. So for example, I'm creating the plot for sine x, where x goes from 0 to 2 pi. And I can also create really simple graphics objects and then build them up into much more complicated graphics objects. So here I have just created a very simple disk of the color yellow. And so some examples of including images and visualizations in the notebook. And why stop with static images? We can also have interactivity in the notebook itself. So again, don't worry about the code, just copy it from the handout notebook, this code that starts with manipulate, and you will see how in this single line of code I can create a simple interface that allows me to play around with the radius of this inner graphic objects, the black disk here, and be able to interact with it in the notebook itself with the help of this slider. So a few different examples of content that can go into the notebook. We had Wolfram language code, we had text, we have images, and we have interactivity in here. Now, what you must have noticed is that when we entered the things in the notebook, they went into these specific cells. For one, you were able to see the in and out numbers here that kind of show where the input was provided and where the output was returned in the notebook. And if you look at the very right end of the notebook, you will notice these square brackets. They delineate the structure of the cells. And you will, as you have seen, a cell can contain the input, the Wolfram language input. It can contain text, it can contain images, and really a combination of all these things. Now, when you just start typing in a notebook, a cell is created by default. So if I click here and then just start typing in right at the top of my notebook, this is the very first cell in the notebook. Okay, so this was as I started typing in, the cell was created. Now by default, every new cell in a notebook will have input style, meaning it is expecting input in Wolfram language. So it's expecting some Wolfram language code. Now clearly what I have here is not Wolfram language code. I was trying to write in text. So you can change the style of the text by using the format menu here. So you can click on this cell and then go format and then change the style of the text of the cell to maybe text if you want, or you can try any of the other cell styles. So for example, I can change it to section if I want to show that this is a section header for my notebook. And you will notice in the handout notebook, I've included in the very last part of slide 6. Let me go ahead and share it with you one more time. There are a bunch of shortcut keys that we have to easily access these different styles of cell. So you can also see them here. Next to the style name, there are the shortcut keys that can be used to change the style of the cell. Now you can also use this, the overhang here that we used initially. We used plain text from here to create the text cells. You can also click other styles of text and you are able to access these different styles of your cell from this menu itself. Okay, now one advantage of having cells of different styles is they provide some automatic grouping of the cells. So if you have different sections in your notebook, so for example, here I can have a section, or rather a subsection, simple examples, and then here I have a different section, image examples, and then lastly here I have maybe interactive examples. Now, these different styles also provide some grouping of the cells. So, all the cells under this particular subsection can be grouped together. I can just double click on the outermost cell bracket, and you see now I can collapse that group of cells. So, I can expand or collapse it as I want to, and this gives me the option to organize my work a little better. Not always have everything open and then spend lots and lots of time navigating through the notebook. I can just have the section that I want to work with open at a time and then leave the other sections collapsed. Another option that's available in the Wolfram language is to actually reverse close a cell. For example, if I want to share this notebook with others and I really want them to play around with this interactive interface and not really worry about the code that was used to create this particular interface, I can reverse close the cell by double clicking on the cell bracket of the output cell. And so now the input is now hidden. I can only see the output. I can always get back to the input by double clicking on the closed cell bracket, and it expands again to show me the input. But otherwise, if I want to, clean up the notebook a little bit and not really worry my viewer or reader with the details of the code, but just stay focused on the output, I can go ahead and reverse close the cell. Before we steer away from notebooks, I want to remind you that the way we evaluate Wolfram language code in notebooks is by hitting Shift Enter. So I can go ahead and edit the code in this particular cell. I can change the numbers around here, and then I have to hit Shift and Enter to evaluate that. And once you have evaluated the code with Shift and Enter, you will notice that this bar appears below the output, which is known as the suggestions bar. And the intention of the suggestions bar is to offer some suggestions for you of what you could do further with this particular output that you have created. So for example, it's asking me, do you want to find out if this number is prime or not? And if I click on that, it shows me the Wolfram language function to test whether a number is prime or not. It's prime q, and it says that yes, indeed, I have the output that I have received is a prime number. So a lot of times beginners find the suggestions bar useful. Sometimes as you get more used to working in the notebooks, you don't really want the suggestions bar. So what you can do then is go ahead and minimize the suggestions bar by clicking this little cross here, and so you are done with the suggestions bar. It will not appear until you go and change the settings again. Now, we've been working on this notebook, but it has been unnamed so far, so we can go ahead and actually give it a name. I can say simple examples, and you will notice it has a .nb extension for notebook, and I will go ahead and click on the little check, and now my notebook is saved as simple examples.nb. And I can come back and work on it. I can also publish my notebook on the web so people can read it. So here's the publish button. I can click on it, and it says that, okay, my notebook will get published to this URL. I can actually give it a specific name, or I can just go with any automatically assigned URL that the cloud provides. I can allow everyone access, or I can password protect it. And so I can go ahead and publish the notebook. Publishing the notebook means it's publicly available. So unless you password protect it, anybody with the URL will be able to access the notebook. I can also just share it with a specific group of people, I can click on share here, and then I can say I can provide email addresses separated by commas, and then I can give them permissions to view only or edit the work, so I can do some collaborative work on the notebooks with my specific group of collaborators. So these are two ways I can share the notebook on the cloud. And from this point onwards, let's move away from the cloud and let's download the notebook and continue to work on it on your own system. So if you click here, you will see it says open this file in Wolfram Desktop, or you can go to the file menu and then use download to download the notebook. I can go ahead and download it. And once the notebook is downloaded, I can go ahead and open it. I have Mathematica on my system, so I am able to open it with Mathematica, and so I can continue to work on the notebook. So I'll go ahead and give you a moment to download the notebook so that you're able to continue to work on it on your local system. And I see there are no questions so far. So I just want to remind you, if anywhere at any point during the course, if you have any questions, please feel free to post it. Okay, continuing in this notebook, let me point out a few things that's helpful to remember while working in notebooks. Um, let's see. So when you start typing in something in an input cell, it will appear in blue until the Wolfram language kernel is actually able to recognize what it is that you're typing in. So I can start typing in RAN, and you see it still appears in blue until I get to random integer, and now this appears in black, which means the Wolfram language kernel knows what I have typed in and will be able to work with it. And along with this change in color, you notice that this auto completion menu popped up as I started typing in, right? So when I typed in up till here, it says, hey, do you want a random integer? Do you want a random image or a random instance, and so on? So I'm able to click from the auto completion menu and able to select what the function name that I'm interested in, just in case I'm not quite sure how exactly to type in that particular function name. And then once I've typed in something like this, I can also hover over it, and I have this little pop-up appear with the downward chevrons and the eye. And so I can actually click on the downward chevron, and what I now get is a menu of the template of using this function. So you can use random integer with all these different types of input. You can give it a min and max, or you can just give it a max, or you can not give it no input at all, in which case it will give you a random integer 0 or 1. And so if you want to quickly see how you can use this function, you can go ahead and click on that downward arrow and see the different options available for using this particular function. And to get more information about a function itself, you can always hover over it and click on the eye, which will bring up the help, the documentation for that particular function. So in this case, it brings up the documentation page for random integer. And these are all interactive notebooks themselves. So you can get into the documentation and go ahead and edit the code there, and then see how things change and be able to work with the function itself, not just read about it. Of course, there's all the information is there under the details, but you can also actually interactively edit the examples and work with them to learn more about this particular function. And then, of course, you can access the help or the documentation from the help menu from Wolfram documentation here. So you should be able to go in and type in some keywords about the function you're interested in, and it will take you to that, either directly to the documentation about that function, or to a list of search results that match the query that you typed in. Um, let's look at some more natural language queries and see how you can use them in notebooks. So go ahead and type in equal to in a cell, and you will notice that it automatically changes to this orange box with the white equal sign, which is a sign from the notebook that it understands you intend to enter natural language input for computation. You're not trying to enter Wolfram language input. You're trying to enter a query in plain English. And so now I can type in something like, give me the population of Denmark. And now the notebook interface understands that, and it also shows me, hey, did you want to something like this? So this is the Wolfram language representation of this query, and it gives me the output here. I can actually access the full power of a Wolfram Alpha search from the notebook itself. So in this case, I type in equal equal, and now I get this spy key with the equal sign, which tells me that if whatever I enter is similar to actually opening up the Wolfram Alpha search engine on a browser and then typing it into the search bar in Wolfram Alpha. So now if I type in Denmark and hit enter, it will give me, just like the example in Romeo and Juliet, it will give me all the computational information that's present on the Wolfram Alpha servers about Denmark. But then the third option is to use control and equal, which gives me this little box in which I can now type in Denmark. And now when I hit enter, my string Denmark gets converted into the country entity in the Wolfram language. And once I have the country entity, the Wolfram language representation of this particular country, at once I have access to many different properties of these entities. So I can go ahead and type in properties, and you see the auto completion menu also working there as well, giving you suggestions for what all you could query about Denmark. And here you can see all these different properties of the country entity available in the Wolfram language. So I can get things like population of the country, or I could get something as simple as the flag of the country. And so I'm able to use this natural language understanding capabilities of the notebook to get much more information than I would have been able to just by using the string Denmark. Again, if you're not quite sure what properties are available, or how you need to get to how do you write this bit of code that gets you the population of Denmark, you can always use the first option that we saw here. You can use the equal sign and say, give me the population of Denmark, or I can even go a step further and can say, give me the population of Denmark's regions. And it's going to understand that and say, oh, by the way, did you want to look at the regions? And not just that, you wanted to look at the population of each of those regions. And so, of course, when I have that information, I can go ahead and use that. You just click on that little box that has the Wolfram language representation of your query, and then you can work with it just like you would work with any Wolfram language expression. So I would go ahead and say, if I wanted to visualize this information, I would just go ahead and put bar chart around it. And so now I can work with that piece of information. Um, in the very last slide of this notebook, sorry, last but one slide, slide 14 of this handout notebook, the basics, I have included a list of notebooks, example notebooks that show you how people have used notebooks to create their content, either some computational exploration or an interactive infographic, or even like an announcement that Wolfram itself has used in the past. So I hope you're able to use these links to access those notebooks to get some ideas of how the finished notebooks can be created and what sort of information can be included in this notebook. So as we wrap up this section, I would like you to click on this link that's there on slide 13, the slide just before the list of neat examples of notebooks. This is the slide right after the natural language computations. And there's a link to a colorful notebook that opens up in the cloud. I would like you to click on make your own copy from the top right corner. And that will allow you to open up your own copy of the notebook in your cloud account. And once you've clicked on make your own copy, I would like you to try out the code in this notebook. Just get a feel of how you can work with Wolfram language code, or if you want to, type in some extra information in a text cell, or go ahead and change the style of this cell. Just feel free to play around with this notebook. Um, and I'll leave you to experiment with that for a little bit. Um, and also, I have a few review questions for this section for you before we move on to the next and the really important part of today's course about the Wolfram language. So, before we move on, I'll give you some time to play around with this notebook, but at the same time, I'll push out a few polls to review some of the things we've been looking at. So my first question is, how do you evaluate Wolfram language code in input cells? Excellent. 100% correct response. You hit shift and enter. That's great. My next question is, how can you share your notebook with others? Do you have to be logged in to the Wolfram Cloud from your browser? Or can you do this from the desktop product itself? Or do you have to use a special function in the Wolfram language? Or can you really use any of these three options? Great. So um, 75% of the folks selected all of the above, which is the correct answer. And two chose from the file menu within the Mathematica or Wolfram desktop. So really, you are able to share a notebook using any of these three options. So let me see if I can quickly go and show you the examples. So yes, you can do this from the menu on the desktop system. So for example, for Mathematica, you will have file and then you can go to publish to cloud, and that will allow you to publish the notebook. From the browser, you have the share and the publish options here. And then we also have the built-in function cloud publish. And if you go into the documentation page for cloud publish, you will see that if you just run cloud publish with square brackets, empty square bracket, it'll go ahead and publish whichever notebook you're working on, the document you're working on. It'll go ahead and publish that in the cloud. Or if you want to be specific, if there's another notebook that you're trying to publish, you can go ahead and provide the pointer to that particular notebook, and you're able to use that to publish the document to the cloud as well. Okay, so my next question is, so we've been looking at this auto completion menu, right, which helpfully pops up with suggestions about whatever it is that you're trying to work with, either a function or the property of an entity. Do you think user-defined symbols can appear in the auto completion menu as well? So far, we've just seen the auto-completion menu show you, Wolfram language functions that are available for use in the Wolfram language in the notebook as you're working in the notebook. If you have defined and assigned values to a symbol, do you think those will pop up in the menu as well? Okay, so I see the majority of the attendees think yes, they will appear, and at least one person thinks no. So let's go ahead and look at an example. So yes, the answer is yes, indeed. So right now, see, test is in blue, which means test has not really been defined, right? So if I start typing in T, E, and so on, I don't see it. It doesn't pop up. But if I go ahead and evaluate this, so now the kernel knows test, it has been defined, it has a value. Now if I go ahead and type in, it pops up here. In fact, if I go ahead and define another one, similarly named, and I start typing in TES, I will see that I have both test and test to appear in the auto completion menu. So that's a helpful feature. If you have lots of variables defined, they will appear in your auto completion menu as you work with it. And the last question for this section, which of the following typed at the beginning of an input cell will indicate to the Wolfram system that you're about to type in a natural language input? Is it star? Is it equal? Is it the greater than sign? Or is it control? Perfect responses, almost perfect responses so far. So it most of you selected the equal sign, which is indeed right. So let's look at the example here for the solution. So yes, if I typed an equal sign, this is what I would get. And then I can type in my natural language query, right? So I can say flag of Denmark. It should give me the flag. Um, if I start typing in with star, if I just click in my notebook and start typing in star, it helpfully converts it into a bullet list. So that's just another text style. And if you click on the cell bracket and go and select style here, you would see it says item, corresponding to bullets in the Wolfram language. So you don't have just text cells, you can also have itemized list of bullet points. And so actually starting a cell with a star converts it automatically into a bullet point. It's just a shortcut to quickly get to that bullet point style in the notebook. And then starting with greater than doesn't really do anything. It thinks this is part of the Wolfram language code you're writing. And then starting with control by itself, or hitting control, just the control button will not really do anything. Of course, control equal will create the box, which again accepts Wolfram language input. Okay, so now we are going to move on to the the third section of the course, and we are going to talk about syntax and programming. I'm going to give you a 1-minute break. So if you just want to, maybe grab a glass of water or a cup of coffee or tea, feel free to do that. Just take a short break, and then we'll get back to syntax and programming using the Wolfram language. Okay, so we have just under an hour to finish up the course. I will keep moving, and we will look at syntax and programming in the Wolfram language. So the learning objectives in this part of the course is really to understand that everything in the Wolfram language is an expression and how we can make sense of these expressions. Then look briefly at how you can represent structured data in the Wolfram language. There are multiple options. You can use a list or an association or a data set. Then we will briefly look at assignments in the Wolfram language, how you can assign values to symbols. And we look at two different forms of assignment, immediate assignment and delayed assignment. we look very briefly into patterns because that's useful in defining functions. And only from that perspective, we are really interested in patterns in this section, in this course. Of course, we can really fill up an entire Wolfram U course with just about patterns. It's just so powerful in the Wolfram language. But we'll just take a brief peek into patterns before we move on to function definitions, and we will see how we can define our own functions, how we can use set delayed to define these functions, and how we can use patterns to specify the input to the function. And we will also take a moment to recognize that while we have the independence to or the freedom to define our own functions, of course there is a huge number of built-in functions available in the Wolfram language. So maybe it's useful to take a moment to search our collection of built-in functions before jumping into writing our own function and reinventing the wheel. um, I have a simple data analysis workflow using some of these built-in functions, which I hope will be useful. I also have a few simple tips to keep in mind as you get more familiar using the Wolfram language before moving on to a few advanced concepts that I would like you to leave you with, understanding how Wolfram language enables symbolic computation and how it also offers the option of using the functional programming paradigm as you use the Wolfram language. So starting with expressions, everything in the Wolfram language is a symbolic expression. Whatever you're typing into the notebook or you write in a script, your all your code in the Wolfram language is made up of expressions. And this is really the structure of a Wolfram language expression. It has a head and it has square brackets, and then it has different elements within the square brackets. Sometimes you will encounter expressions in the notebook that looks very different. It might not have this very specific structure. You might not find a head or the square brackets or elements within the square bracket, but we'll come to that in a bit. For now, let's take a look at few examples of expressions in the Wolfram language. If you want to, you can go ahead and evaluate and see what the output is, but you don't need to do that right now. All I want you to do is look at these expressions in the Wolfram language and see if you can spot some sort of similarity, some sort of common features across these different expressions in the way they are represented in here right now. So there's something like date string. As the name suggests, it will give you the date in string format. Then there's list plot, which is a visualization function. Histogram, again, as the name suggests, will create a histogram. And a bunch of other functions, other expressions. All right. What you might have noticed that they do look similar in that they often begin with a word that starts with a capital letter. They all have square brackets and they have elements within the square bracket that are separated by comma. And sometimes there are no elements within the square brackets. Now, these fit in nicely with our view of an expression in that it has a head, it has square brackets and stuff within the square bracket. But now let's look at a few examples of Wolfram language expressions that look very different. For example, a plus b. This is a valid Wolfram language function, but it doesn't really have that structure. It doesn't seem to have a head or square brackets and so on. However, we can use something called full form in the Wolfram language. And I apologize for the typo there. You might have FUL, FORM. It should be FULL, FORM. This is a built-in function in the Wolfram language. It allows you to see the underlying structure of every expression. So although a plus b does not have that look that we saw in the previous slide, if we do full form of a plus b, we will see that really underlying a plus b, as we see it here, is this expression which says plus and then within square brackets a comma b. So an example how what you see in the notebook is not necessarily what the kernel sees. It Even if you see it in this nice arithmetic form, just a and b being added, underlying it is really, again, the same structure of the expression with a head and then square brackets. Here is what is known as a list in the Wolfram language. Is enclosed in curly braces a bunch of items. So it's a list of items A, B, C, D, and E. Again, it does not look like an expression as we saw in the previous notebook, previous slide, but then again we can look at the full form and we will see that indeed it has a head, list, and then within square brackets are its elements. In fact, this nice plot created here also has this structure. And so I can go ahead and look at the full form and I'll see it has a head, and then within it, it has this very nested, complicated structure. But overall, you will see it's the same structure. It has a head and then a bunch of items within the square brackets. Those items themselves are again expressions with their own head and their own square brackets and things within the square bracket. Um, if you quickly want to figure out what is the head of an expression, you can use the head function. So I have an expression here, a plus b by 2c, and I can use head on that expression to see what is indeed its head. It says plus it is its head. And I can also look at the full form of this expression. I can confirm that yes, indeed, that at the topmost level, the head is plus, and then it has some stuff within the square bracket. It can be a single element or it can be an expression itself. Now, these single elements, right? These are the basic building blocks of the Wolfram language. They are known as atomic elements of expression. So, like all other programming languages, Wolfram language expressions are ultimately built from this small number of atomic elements. I have only few examples here. There are many more atomic elements in the Wolfram language, but the standard numbers, so a basic integer, a rational, a real number, or even a complex number. These are all atomic elements in the Wolfram language. And then we have the strings, which are enclosed in quotes. So anything within double quotes is treated as a string. And then we have the symbols. So the symbol is the basic named object in the Wolfram language, something that you would call a variable in another language. So the symbol has a unique name, which is a concatenation of characters, but it cannot begin with a number. So here are examples of symbols here. You will see they are all blue because they have not been defined yet, as in I have not assigned any specific value to this symbol. It just exists as that name itself. There are some rules to naming symbols that one, of course, it has to be a concatenation of letters, numbers, and characters. It cannot begin with a number, and it cannot begin with certain reserved special characters as I've listed here. So as long as you keep track of those rules, you are free to name your symbol in any way you want. So you have numbers, you have strings, you have symbols. You can put all these together to build more complex expressions, which are called composite expressions. So for example, here is a composite expression that was built up from multiple atomic expressions. So I have strings here, I have numbers here, I have lists of numbers here. And so I have built up this expression from the basic building blocks of atomic elements and nested expressions to create this entire composite expression. And here's another example of a nested expression. So here's one expression that gets a random real number, and then that is provided to another expression which has the head 10, another expression which has the head exponential, and so on. So it forms this complex composite expression by nesting expressions. So why am I spending all this time on expressions? Because I would like you to walk away from this course with an understanding of expressions being a crucial unifying principle in the Wolfram system. The fact that every object in the Wolfram system can be expressed similarly, as an expression, allows the language to do so many different things with a comparatively small number of basic operations. So when you see an expression, there are a number of different ways you can really interpret that expression. Here again, another example of that simple form of the expression we saw previously with the head. Here, F is the head, and the square brackets and elements within the square bracket. So the different ways the head and the expression itself can be interpreted are, you can have it as a function where f is really a function, and then x and y are the arguments or the parameters of the function. For example, if you had to find the sign of x, then sign is the function, and then the input argument is x, the element that is provided, for which you want to calculate the sign. Or f can represent a command, and x and y are again arguments and parameters. So for example, I have an algebraic expression x plus 1 raised to the power 2. I want to expand it, and so expand is like the command I want to use for this particular input. um, f can be interpreted as an operator with the elements within the square bracket as the operands. For example, we saw x plus y plus. The head plus is really standing in for an arithmetic operator, and the operands are x and y. And then it can just be, just be the head of an expression. For example, in the list we saw, it's not really doing anything. It's just saying that this is a list of three different elements, x, y, z, and the head is list. Or it can also represent the type of object. For example, in the Wolfram language, RGB color is represented with the head RGB color, and then within the square brackets, you have the red, green, and blue values for that color. So I can actually go ahead and evaluate you, and you can see that this is what you see on the notebook, but this is really represented as the expression RGB color, which specifies what type of an object is it, and then gives you the parameters of that object. So you have 1, 0, 0 as the red, green, and blue values for the RGB color. So far we've mostly seen all expressions in this standard form, the head, square bracket, and elements within the square bracket. There are at least two other ways to provide input to input expressions. So for example, if you wanted to find the mean of three numbers, 1, 2, 3, you would have gone and written mean as the head here, and then within square brackets you have 1, 2, 3, and here we are using like the function interpretation of the expression. So I want to compute the mean of this input. I would go ahead and type it in like this. Or the example we saw on the previous slide, find a random real number, compute the tan of it, compute the exponential of it, compute the cosine of it, and then compute the sine of it. Now, the same expression can also be written in two other forms called the prefix form and the postfix form. In the prefix form, we provide the function name here and then use the symbol at as a prefix to the input to the function. Okay, so mean at 1, 2, 3 will do the same job as mean within square brackets 1, 2, 3. So similarly, whatever was being done with sine on cos and x and tan of this expression will also be done by this expression here, where I'm not using the square brackets, but I'm using the prefix form using the at symbol. And the second way of inputting the same expression is using the postfix form, where the function is being used more of as an afterthought. I have a list of numbers, and then I decided, I want a mean of these numbers, and so I can go ahead and use the postfix um, um, operator, the // and then follow it up with the function name. So 1, 2, 3 / mean will also do the same thing that's been done by mean of 1, 2, 3. And so now my standard form expression from here in the postfix notation looks like this. I create a random real number, then I find its tangent, then I find its exponential, its cos, and its sine. And this is the way I build up the expression. Now you can think of any Wolfram language expression as a tree. We have seen the full form of expressions. We can also use tree form to print out the expression in the tree structure. And this gives us a clear picture of how expressions are built up in the Wolfram language. So you have at the bottom level, you have the individual atomic elements that were put together with plus here, and then the result of that was put together with 2 with power, and on the other side we have x being raised to the power 3 here, and then that was again put together with the plus here, and the entire expression was created. So tree form is a nice way to quickly visualize the structure of the expression. So we see this expression is created of these multiple different parts, and wouldn't be it be nice to access the parts of the expression? So we can do that in the Wolfram language using the part function. So if you have any expression and you want to access a specific part of that expression, you use the part function. And so I can get to the second part of this expression. I set it up this way: say part of this expression, give me the second part of this expression. And instead of having to write part every other time, you can use a shorthand notation for the part function, the double square brackets. So basically, it's a way to index into this particular expression and pull out that particular part specified by that index. So give me the second part of the expression with double square brackets. I say it should pull out y. Now, why did I go ahead and use the parenthesis here is that if I didn't use the parenthesis, it would go ahead and try to get the second part of only z. That's not what I want. I really want the second part of this entire expression, and so I had to use the parenthesis to avoid that confusion. Now, it's just not the part at a particular level. I can drill in deep into multiple levels. So here you see I have this expression here, and its second part consists of this entire part. And then I want the first part of that second part. And so I can say, give me the first part of the second part, and it will pull that out. Now, since a list is also a Wolfram language expression, I can apply the same reasoning, and I can use the part function to pull out parts of the list. And this is just a list of XYZ items. And then if I wanted the third item, I will use the part function with the index 3. In the Wolfram language, indices start at 1. So 1, 2, 3. I would get the third item using the index 3 and using the part function. Okay, so this brings us to lists as a way of representing structured data in the Wolfram language. Lists are ubiquitous in the Wolfram language. You'll find them everywhere. Here are two examples of lists. One shows items of all of the same type, 5 integers. And here is another one that shows you that lists can really collect things of many different types. It doesn't have to be of the same type. So you can use the list as a container of items, as a set, as a vector or a matrix. It can be just a list of variables or expressions. You can have a list of colors here. You can have a list of numbers. You can have a nested list representing a matrix of integers. And actually, this looks nicer with matrix form around it. And the person sign really refers to the last output. It's a shorthand notation to access the last output created in your notebook. And so you can see that this nested list actually really represents this matrix here, with each row as each inner list, and then the columns are the rows stacked on each other. And as you saw in the previous example, you can use the part function to pull out elements of the list. So if I want the second element of the list, I can say, give me part 2, or I can use the shorthand notation with the double square brackets. So here is my list. Okay, so my list of A, B, C, D, E is being stored in my symbol, my list. And then I can use the part function to get the second part of the list. I can index from the end with negative indices. So give me the last item, which is -1 from the end. It'll give me the last item. I can get a span of indices from 3 to 5 using the double semicolons. I can go from one index right to the end, again with the span, but nothing at the end. So it's as from 4, give me right up to the end. It will give me items from the list. I can pick out specific items from the list using a list as the index itself. So give me only items 1 and items 4. And so I can pull those out from the list. So very short overview of what you can do with the list. You will find much more details in the tutorial about lists, and it is linked from the references and right at the end of this slide. Moving on from list to another way of representing structured data in the Wolfram language, associations. Associations allow you to represent data in key value pairs, so a dictionary data structure. Now you have the advantage of using the key to access the value rather than having to remember the index at which that particular data item occurs in your list. So for example, I have a list of students and then I have a list of their quiz scores. Now, if I want to get Charlie's score, I have to remember that Charlie was student 3 in my list, and so I need to get the third quiz score from my list, which can be a pain right now. But I can do that to get to this quiz score. But it would be nice to associate each score with the corresponding student. And so for that, I can create an association in the Wolfram language. It has this special syntax. It has the greater than sign, the less than sign, and the pipe to open, and the pipe and the greater than sign to close the association. And within it, I have the keys that point to the value with the arrow. And you get to the arrow with the hyphen and the greater than sign. So if you click this, it becomes the arrow in the Wolfram language. Okay, so now I have the quiz score saved against each student name in this association, and now I can just query the association with the specific key. If I want Charlie's score, then I just say student quiz scores and give it the key that I want, and I can go ahead and change that to another student name, and now I have their score. You can build an association from scratch. You can use the association head and then build the association this way, or you can use the special syntax with the pipe and the greater than less than signs. And once you have the association, you can use the keys to access the values of the association. Any valid Wolfram language expression can be used as a key, but if you want to hold on to the values of your in your association, the keys must be unique. So if you repeat the key, then the value of the previous key will get overwritten, and only the value of the second occurrence or the last occurrence of the key will be retained. So if I add another key, A, to this particular association, this value might get overwritten, and the last value that I have, only that will remain. Many Wolfram language functions provide their output in associations. So for example, counts, which counts how many times an element appears in a list, will return an association. Similarly, letter counts, which counts how many times a letter occurs in this case, in the Wikipedia article about computers, it will also return an association. Two quick useful functions that gives all the keys or all the values in an association are keys, which pulls out all the keys of an association, and values, which pulls out all the values in the association. A dataset is used in the Wolfram language to represent hierarchical structured data. So here's a simple example of a dataset. So what you need to create a dataset is either a list or association. So you can have a list of lists, list of association, association of association. And then once you wrap data set around it, you have this nice formatted presentation with the column headers and the row headers if you choose. You might not have row headers if you want, or you might not even have the column headers, but you have this nice formatted representation of the data, any hierarchical data that can be created with the data set. And once you have the data in a data set, you can then do database like query operations on the data set. So you can either get individual named rows by providing the names of the rows. So I can get from row B, I want column Z. And so I provide those names and I can get the element. Or I can get entire row B, all the columns X, Y, and Z. Or I can get all the rows for column Z. So I get both rows A and B for column Z. And anywhere we can ask for a part in the data function, I can also provide a function that can be applied to that part. So I can, so if I got all the rows and then Z, I can now say, give me a pie chart. And what it'll do is for those rows, it will create a pie chart with all the columns in that particular row. Or if I have all the rows and I want column X, I can then actually go ahead and create a total of all the rows for that particular column. And instead of all, then I can use total here in the data set, and it will give me back the total of all the rows for that particular column. So it might take you a while to get used to working with data set. It needs some time spent on it. The best option would be to actually go into the documentation for data sets, and then spend some time here looking at the various examples, playing around with it, especially I feel in this section of the documentation, with the options section. So then um, go in there, try the different options and see how you can work with data sets, the application section, so where you can see how you can create a data set from a list of association or an association of association, or other more nested structures of the data. So you might need to spend a little time in the documentation here to get the hang of how you can use data sets. But once you get comfortable, data sets allow you that option of performing these database like queries on your data set, and working with it. Okay, let's have a quick review of the topics we've covered so far. um, so do you think it's true or false that all Wolfram language expressions have a head? We've looked at multiple examples of expressions in the Wolfram language. Do you think all of them have a head? Okay. So again, the majority agreed that that's true. And then one person felt like maybe no, not all Wolfram language functions have a head. So the right answer is yes, true. All Wolfram language functions have a head. So the quick way to check this is by using the built-in function helpfully named head. You can just use it on any expression of your choice and you will find the head of that expression. So even if I have a single symbol, I'll see that its head is actually symbol. For a number, you see it says integer. For a string, it says string. In fact, I can go ahead and create a notebook, and this is a notebook you see I just created. Even that has a head called notebook object. In fact, the notebook you're working on right now, that can be accessed with this with evaluation notebook. If you run head on the evaluation notebook, you will see it is also actually an expression, and it has the head notebook object. Okay, let's have another question here for you. Which of the following is a valid symbol name in the Wolfram language? So you have a few different options there. ABC1, 1ABC, ampersand ABC, star ABC. Which of these will be accepted as a Wolfram language symbol? Correct. Everybody got this right. It is ABC1. You cannot start with the number. You cannot start with those special characters, ampersand or star. Which of these statements would you agree with? Which of these do you think is correct? User-defined symbol names have to start with small letters. Atomic expressions, examples like integer, real, do not have a head. Expressions can be nested to form composite expressions, or built-in functions are not really considered expressions. All right, so let's take a look at this. So the right answer here is that expressions can be nested to form composite expressions. This we can disagree with right away because we just saw that every expression in the Wolfram language has a head. So whether or not it's atomic, it will still have a head. Um, Built-in functions are not considered expressions. That cannot be true because everything in the Wolfram language is an expression. So even built-in functions are expressions. Um, User-defined symbol names have to start with small letters. While it is recommended that you have, when you are defining your own symbols, you start with a small letter in order to differentiate and create less confusion for your reader as to which of the functions that you're using is a built-in function in the Wolfram language and which ones are your custom defined functions. It is usual practice among Wolfram language users to have their own symbol names starting with small letters, but there is no hard and fast rule, as in you will not get an error if you define your symbol starting with a small letter. So really, the only statement that is correct here is that expressions can be nested to form composite expression. And the last question from this section is select the snippet that shows the correct Wolfram language syntax. Is it list 1, 2, 3, dataset 1, 2, 3, association 1, 2, 3, or really all of them are correct? Okay. So yes, it's only this one that's correct. While in many of the previous responses, all of the above has been a safe choice, not in this case, because if you just go ahead and try this out in your notebook, list 1, 2, 3 is really the full from representation of a list, the one that you have seen with curly braces. Data set 1, 2, 3, you will see, while it'll come back as an expression, this is really incorrect syntax for representing a data set. If you go into the documentation for data set, you'll see you either have to have a list of lists or a list of associations or an association of association to be able to successfully create a data set. And then, of course, for associations, we know that we have to have key value pairs. So you can't just have a single elements in an association. The essence of an association is that it has to have key value pairs so that you can later use the keys to access the values. So of these options, list 1, 2, 3 is really the only correct syntax here. Okay, moving on with our syntax and programming section, now we get into assignments. So we've been looking at symbols. How do we assign values to symbols? So there are two options here. You can use set or set delayed. Set is the usual assignment that you might have seen in all other programming languages where we use the equal sign. So the way we set up an assignment in it's like a rule of the form. You have a left hand side, and then there's the equal sign and the right hand side, which means that right hand side will get evaluated right away, and then that value will be assigned as the value of what you have on the left hand side. So x equals 3 will assign the value 3 to x. And now if I say a is equal to x squared, instead of x, the system is going to use the value 3 because that has been defined as the value of x, and it's going to compute x squared and assign that value to a. For delayed assignment, the rules are implemented a little differently. And the way delayed assignment is set up is you have left hand side and you have colon equals right hand side. The right hand side is maintained in an unevaluated form. Whenever the left hand side appears in an expression in the future, only then it is replaced by what was there on the right hand side, and this is evaluated anew every time. So if I go ahead and set up this assignment with delayed assignment, b is colon equal x squared, then whenever I ask for b, it's going to go ahead and see, oh, it's x squared. Oh, by the way, what is x? Remember here I had set up x as 3, and so then it's going to go ahead and calculate 3 square, and it's going to give me that value. Now if I go ahead and change the value of x, I set it now to 2, and now if I call a, you see that I still get back 9. Why is it so? Because when a was calculated, x still had the value 3. And so it calculated 3 squared, that is 9, and it assigned the value of a as 9, and that is set. That is going to be the value of a forever till I go ahead and change it. But for B, because I had set it up with delayed assignment, it had only saved the value of B as x squared, not as 9. And so now if I go ahead and use B or call B, it says, okay, x squared. By the way, what is the value of x? It's 2. Okay, 2 squared is 4. And so now I have the value of B as 4. If you use the information operator or the question mark on A, you will see that the value of A is really 9. It's a global symbol with a value 9. But if you use it on B, you will see that B is stored as x squared. So it's going to wait. Whenever B is used, only then it's going to go ahead and see, oh, I need x squared for B, and it's going to look up the value of x and calculate x squared. So this is the difference between set and set delayed. We are going to end up using set delay to define your own functions, but before that, a very brief uh, detour into patterns. So we know how to recognize patterns in the Wolfram language and are able to actually use it while defining our functions. Um, Again, as I said, there's a lot more to patterns, and you will really like the tutorial we have here. So if you go into the documentation by clicking on any of the links about patterns in the notebook, you can go to tutorials and you will see there's introduction to patterns. So if you're really interested in how to work with patterns in the Wolfram language, I would highly recommend this tutorial. But for now, let's just know that patterns are represented in the Wolfram language using blanks. A single blank represents just one thing. So for example, if you're looking for an expression with the head f but only one argument, you would use just one blank, and so only this expression would get picked up. Okay, what I'm doing here is actually replacing. This is the shorthand representation for replace all, a function in the Wolfram language that allows me to replace something in an expression with something else. So it allows me to replace the left hand side with the right hand side. And for the left hand side, I'm using a pattern which says, give me an expression which has the head f but has only one single element within the square bracket, and replace it with xxx. So a single blank stands for one single element, just one thing. But I can also use the pattern for one or more things, in which case I use double blanks or two underscores. It's called the blank sequence. Now, if I use this in my pattern, it means give me an expression with a head f, but with one or more arguments. So it should match both this one, which has one argument, and this one, which has two arguments. And so it works that way. I have yet another blank sequence. It's called the blank null sequence, which can stand in for zero or more things. And this is uses three underscores. Okay, so now when I use three underscores, it's looking for an expression with head f and zero or more arguments. So it should match this one, which has zero arguments. It should match this one, which has one argument, and it should match this one, which has two arguments. So this is how patterns are represented in the Wolfram language. You can go ahead and name the pattern by sticking a name in front of the blank. Okay, and you'll see an example in the very next slide. And you can also restrict the pattern. So, okay, it's a blank. It can stand in for anything in the Wolfram language, but I like that anything to be at least an integer. And so I can specify the head after the pattern, after the blank, to restrict the pattern. So it should only match something that is an integer. And so it should match 3, but if I'm looking for a real, then it shouldn't match 3, right? But it should match 3.14, which is a real number. If I am looking for an expression with head f, then I can put that head behind the pattern, behind the blank. And so this should match an expression with the head f, but it should not match an expression with a head g, for example. Okay, so this really stands in for something like this that we just used in the previous 3 examples. So you have explicitly created the standard form with the head and the square bracket and something within the square bracket. You can use it in the shortened form like this, with the head following the blank. Another way of restricting patterns is by using predicates. Predicates are useful functions in the Wolfram language that can test something as true or false. So, for example, I can test whether this is a number. I can test whether this is a number either. So, because this is a string, it gives me false. Um, if it's indeed a number, it gives me true. So, you will find most predicate functions in the Wolfram language ending with Q. So if you were to search up for functions ending with Q, you would know these are predicate functions. So I can test a pattern using that predicate and then the question mark. So this is like a pattern test. So match the pattern and then test if it is actually a number. And so give me true only if it is a number. And so then this will be true, but for a string, it will be false. I can also match multiple I can have multiple tests on my pattern. So I can say, give me either if it's negative or um, sorry, it's an and. So give me a negative but even number. So this shouldn't be true, but this um, sorry, let's go ahead and evaluate this. I confused myself there. Okay, so what this is really testing for is it needs a negative number as the first element of the list, and it's really testing for a even number as the second element of the list. So please ignore this text here right now. That is not the best description of what this match is doing. Okay, so I can in this way I can restrict my patterns, and then I have some links to multiple different predicate functions that you can check. More of it are testing expressions here. And then one final way of restricting patterns is by using conditions. And this is the condition operator here. And this is where a named pattern becomes helpful. As you see, I've stuck something before the blank, which is naming the pattern. So match anything, any Wolfram language expression. But I'm going to go ahead and call it X. And then once I've matched, I'm going to test if X is greater than 0. If that condition is fulfilled, that I'm going to return a true for my match. And so this will return true, but this will return false because um, my expression is actually negative. So the condition is yet another way of restricting patterns. So in these different ways, you can restrict patterns. You can restrict it on a specific head. You can So we restricted it on a specific head. You can restrict it with predicate functions like number queue. There are a host of these other predicate functions, string queue, possible zero queue, so on. Um, and then you can restrict it using an expression. And so you can use these restrictions to actually restrict the patterns that you use as input to your function. Let's take a look at those examples. So how do we define functions in a Wolfram language? The notion of a function is really more general than any either traditional mathematics or computer science. In the Wolfram language, this is considered a function, whether it evaluates to something definite or it remains in a symbolic form. Either way, this is still a function. And while you can do a lot with the built-in functions, you do want to define your own functions, and then they are defined in usually this way. With the set delayed, you have the left-hand side, which is typically the name of the function and has a syntax that to show how it is used. And on the right-hand side, you have the function definition. What are you going to do with the input provided to the function? Becomes much clearer when we use examples. So this makes a simple disk. Okay, this is graphics disk. Okay, now if I wanted to change the color of the disk, I would have said maybe orange. If I want orange, I want an orange disk. Okay, so now every time I want a disk of a different color, I would go ahead and copy my code, change the color to green. I would get disks of different colors. But maybe I can go ahead and make my own function where I will specify the color and it will create the disk of that particular color. So I call my function make disk, and then I use square brackets, and within it I use a pattern to signify the input that will be provided to my function. It's going to be a color. Now, that doesn't really mean it's expecting a color. I have just named it color, right? I can just provide anything I want at this point to this function. But notice that I've used a pattern. So it's kind of a stand-in for any input that's going to come into the function. I call it color. And because I've named it, I can now use it on the right hand side to describe what is to be done with color. What is to be done is really a disk is going to be created of that particular color, and graphics is being used to um, create that disk of that color. I can define that function. You'll notice nothing has happened. Remember, what happens with setDelayed is the right hand side is simply stored as the definition for the left hand side. Now, when I go ahead and actually use the left hand side, the right hand side will be invoked. And if I provide a color, it's going to create a disk of that color. If I say light green, it creates a disk of that color. So a very simple example of creating a custom function where you provide an input and then do something with that input. Now, setDelayed is a convenient choice is because when you define your own function, you may not want either the left-hand side or the right-hand side to be evaluated. Right? You just want the definition to be recorded. So here's an example where I'm defining a function that will come up with a polygon of random color and random number of sides. Okay, so it's going to come up with a random color, and then it's going to create a regular polygon of a random number of sides between 3 and 10, both included. Okay, now I can use this function to get a random polygon. Now, if I had not used setDelayed for defining this function, I went ahead and used just set, where I'm just using equal sign. What's going to happen is this. Okay, immediately the right hand side gets evaluated, and so I get back this regular polygon. In this case, it looks like I have a polygon of 8 sides, an octagon, and then it's brown in color. Now, no matter how many times I use this function, I will always get back this brown polygon. This is not what I had intended. I want to build this as a function so that I am able to get a random color and a random number of sides every time I use this function. And this is the reason I need to use it with setDelayed, because here, if I use it every time, I get back the different random color and a different random number of sides between 3 and 10. So I hope this shows you why setDelayed is the more useful option for defining a function. We can always look up the information. We'll see that while random polygon actually stores the right-hand definition unevaluated, what happens with give me another random polygon, it's hard coding the random color that was generated during definition and the number of sides that was generated during definition. So here's another example where you see this is a classic computer science exercise, writing your own functions to find the factorial. So I define a rule for the base cases. So factorial of 1, I set it up as 1. I know I've used colon equal here. You could have used equal because it's not going to change no matter what I give. Factorial of 1 is always going to be 1. And so now I have factorial 1 as 1. But if I ask for factorial 10, it comes back unevaluated. That so far the system doesn't know what to do with 10. It only knows what to do with 1. If you give it 1, it can tell you it's 1. If you give it something else, it doesn't know what to do with it. That's when we have to define our own function. And this time I'm going to use a restricted pattern to say, only if my input is an integer, I'm going to compute factorial 1 in this way. I'm going to compute factorial n as n times factorial of n minus 1. So I go ahead and define that, and I can calculate either factorial of 10 or factorial of 1000. Okay, but what happens if I ask it for factorial of it doesn't know what to do with it. So it just comes back unevaluated. Now I can set up a rule to catch such erroneous inputs. Because I have a rule of anything underscore integer defined, I can set anything underscore, which is not a restricted pattern, as input is not an integer. So the string will be returned. So anything that matches the pattern of an integer will automatically return the actual factorial, but anything that is not an integer will return this message. And so now if I look at fact, I will see that these are its definitions. Okay, let's have another quick review and then we will finish up the last section of the course. So select the correct syntax for applying a function f to arguments arg. The right syntax of using a function on its argument in the Wolfram language. Right, so the correct solution is the single square bracket. So if you have a function and you want to apply it to arguments, you use single square brackets. If you set time as time colon equal now and then use the symbol 3 hours from now, what will be the value returned by the symbol time? Will it be the time when the assignment was made? Will it be the time when the symbol was invoked? Or will it return an error? Or will it return an error in that it will say set delayed cannot be really used for symbols, it's only used for functions? Or is it going to return an error because now is not a valid Wolfram language function or a Wolfram language symbol? That's great. All the responses have selected the right answer. It is indeed the time when the symbol is evoked. So if I say time colon equals now and then now evoke, it's it gives me the time uh, um, now really, and then if I have time and then again you can see every time I invoke time the value changes because now was never really evaluated. It gets evaluated every time I'm invoking time. Okay, if a function has been defined as fx is colon equal 1 by x, what is returned when I evaluate f of abc within quotes? Okay, so this was a tricky one. Let's actually take a look at the solution in the notebook itself. So now if I'm going to go ahead and define, so I'm going to clear f in case I've used it before. I'm going to define f of x as 1 by x, and then I'm going to give it the string. Now, if you thought that it should come back as f of abc within quotes, doesn't because I haven't really imposed any restrictions on the pattern. So it will go ahead and do what it can with x. So it will actually give me 1 over abc, but whether that makes sense or not is really not the system's concern. You wanted 1 by whatever input you gave me. I returned to you 1 by whatever input I got. Now if you've selected 1 by abc as option A, well, it looks like 1 by abc here, but if you copy and paste it into your notebook, you will see this is only the output form. So just to make it look nice and pretty, the strings appear without the quotes in the output form, but if you copy and paste it, you will see the quotes actually exist. So it does appear as 1 over within quotes abc. All right, so let's quickly finish off that last little bit. I know we are running a little late, but I would still like to finish this last bit. I feel it provides a lot of helpful information. So I did have very small section about built-in functions. There are over 6,000 built-in functions in the Wolfram language. And then I have a very small workflow using the built-in functions, but unfortunately, I won't be able to go over it today. I invite you to just work through this code, evaluate it on your own. You will just see it's really simple. It uses import to import some text from a website, wolfram.com, and then it uses the built-in function text cases to find all the nouns from the text on that website. Once you have the nouns, it sorts them by the number of times it occurs and takes the largest five most frequently occurring nouns on that page, and then it creates a bar chart, so a visual representation of those words and how many times they occur, and also creates a word cloud out of those nouns, so a visual representation again of how often these words appear on the web page. And then finally, it shows you an example of how you can cloud deploy a form page, so that you have a web form where if you give a URL, and again, you can do that error checking very automatically by specifying that the input you want has to be a type of URL, and you get that URL, and then you import the data from that web page, all the text from the web page, and do exactly the kind of analysis you did here in the notebook, but you have this analysis deployed to the cloud so that it happens when someone provides an input for the form page, and then creates the two visualizations, the bar chart and the word cloud, and shows it on the page itself. If you click on the link, you will see an example of how this should appear, but you are welcome to try it out on your own here. I do want to finish up with two important aspects of the Wolfram language: the symbolic programming and the functional programming aspect. But before that, there is this short list of useful tips for the language itself. A reminder that there are four kinds of brackets in the Wolfram language. There's the square bracket that you've seen for functions, curly braces for lists, double brackets for indexing using the part function, and then parentheses really for grouping operation. In addition, I have included some tips and tricks to really keyboard shortcuts that can be useful while you're working in notebooks. Nothing much to explain here. I'll leave you to go through those tips and tricks, and hopefully you're able to use them as you're working in the notebook itself. But I want to end with a few words about symbolic computation in the Wolfram language, how everything is treated as an expression, as a symbolic expression at that. So here X is just a symbol. Actually, I think we had used X before. I'm going to go ahead and clear it. So now you see it turns blue. So X is just a symbol, and they can be undefined. You don't have to define a value to X, but you can still use it for computation. And that's why you can any expression represented in the symbolic form, you can work with it in the Wolfram language so easily. So other things are also represented symbolically, whether it's an image, whether it's an entity, whether it's a graph. You can have a list of these symbols. You can use a function on the symbol. So you can have f of x. We had defined f, so I need to go ahead and clear f. Okay. Now, instead of your own function, I can use something like framed. I can use it on the symbol. I can use it on the image, on the graph. I can really use any Wolfram language function on any Wolfram language expression as long as it will accept it. So here I can actually create a frame around the entire list, or I can put a frame around each item in the list using something called map, which allows me to work on individual elements of the list. So it maps the framed function on individual items of the list. So you can use map to do things to items in the list. And often there are also functions which are themselves listable. So you don't have to use map, but you can use a function and it will work just as well on a list of items as it will on an individual item. So you can look up listable and it will show you some examples of functions that can do this. And with this symbolic character, the Wolfram language also supports extended form of functional programming, functions that implement or represent such functional operations that they can operate and on the data, but also on other functions themselves. So here was an example where we map framed on other expressions. And here is the shorthand notation for map /add. There's another functional operation, apply. What it does, it is actually goes ahead and replaces the head of an expression. Again, let's go ahead and clear A and B as well as C here. So what F apply will do is replace the head of this list here with F. So we know the head of this list is list. It's going to get replaced with F. And so now I have F of A, B, C. So you can see I can create the total of each inner list here by applying plus at the level 1. There's also a shorthand notation for plus, which is worth exploring. Now, with these functional operations, using pure functions makes it really nice to apply any function at random on the fly on a list of items. So the way you build a pure function in the Wolfram language is with this special syntax with the ampersand and the hash. The hash is the placeholder for any input you will provide to the pure function. So this is my pure function. I can use it on one input. So I provide my input within square bracket, and you see here, instead of a named function, I have a pure function with this special syntax. So it can accept any input and work with it. It can also be applied on a list of inputs using map. So this is the shorthand notation for map. So I have a pure function. Now it will work on each individual element of a list. Okay, here I have a pure function using the built-in function frame, but look, I have specified the placeholder with the hash. So basically, I want a frame, and then I want the background of any random color. So this is my customized version of framed. And now I can map it over elements of my list. Now, pure function can take a single argument as input, or it can take multiple argument, in which case you number the hash. So instead of just hash, you have hash 1, hash 2, and hash 3, and then it is able to accept the inputs from the inputs you provide to that particular function. And I'm going to end you with some examples of doing things repeatedly. Unfortunately, I don't have the time to go through it today. So I have just mentioned a number of functions that you can use to do things repeatedly in the Wolfram language. It's different from the usual loop the loop approach of doing things repeatedly in other programming languages. So as soon as you think of repeated operations, you think loop. But in the Wolfram language, there are these other ways of actually doing it. Map is one of it. So you saw how you can repeatedly do the same operation on items of a list by just mapping the function on the list. You can also use things like table, nest, or fold to do these things. So I hope you're able to explore those options. If you have any further questions on these topics, especially the ones at the end that we couldn't get into as much details, feel free to write back to me at wolfram-u@wolfram.com, and I would love to get back to you on the to answer those questions. I do see there was one question from Francesco about why we need the question mark in this case. I believe that was from trying to find out about the definition. So question mark is the information operator. So if you go into Wolfram documentation and you search for question mark, so you will see it's really, it gives you the definition of the function. So so if I define a function and I want to quickly look up the definition of the function, I will use question mark and then the function name, and then I get a quick view of how the function has been defined. I also hope that you're able to work through this last notebook that was part of the handout. If you get into it, you will see you have the question, and then you have a lot of hints that give you actually links to documentation pages on functions that you should be able to use. And then once you have tried things out on your own, you're satisfied with it, you can go ahead and click the solution button to compare your solution with the recommended solution, or one example of a solution that we have provided in the notebook itself. So I hope you're able to work on those exercises to get a flavor of working with the Wolfram language. We will end the session here today. I understand I ran out a little bit of, at the end, I ran out of time a little bit, and I do apologize for that. But I do hope you are able to walk away from this session with some useful ideas about how to use the Wolfram language and other aspects of Wolfram technology. There's a very brief survey once you exit the webinar. So if you wouldn't mind taking that survey and giving us a little feedback about the session, that would be really very helpful. Thank you for attending the session, and I hope you have a wonderful rest of the day.